Hello everyone and welcome to part 3 of chapter number 1, Physical Quantities and Measurements. And in this part we are going to study about the scalar and vector quantities. So let us break down the physical quantities into two types, one of them being scalar and one of them being vector. So before we start this one, I always start this topic with a question for my students that if we have a box, suppose there is a box and I say a force of 5 Newton. I have a force of 5 Newton that is being applied on the box, and that box is, let's say, placed on the table or something. So a force of 5 Newton is being applied on the box that is placed on the table. What would be the direction of motion of the box? Would it move forward, backward, upward, downward? The answer to that question is we don't know. We don't know if it would move forward, backward, upward, or downward, or will it even move at all. The thing is, unless we are given with the direction of force, we can't answer the question. So, for example, if someone is pushing the box to the right side, so it is uh, very likely to move to the right side. If it's not heavy enough, and let's assume that the person is able to move the box with a force of 5 Newton, then the box has to move towards the right side. And if the force of that 5 Newton is being applied to the left side, I'm pushing the box to the left side, then the box would move towards the left side. So the same force of 5 Newton can move the box in every possible direction depending on the direction of the force itself. So for some quantities, we'll conclude that for some quantities, you have to mention direction as well for their proper description. Force is one of them, and matter of fact, all such quantities for which you have to mention direction for their proper description, for their proper understanding, for their proper like working, those quantities are called as vector quantities. So in the first row, I'm going to differentiate between scalar and vector quantities. So for the scalar quantities, they are represented, these quantities are represented or described by magnitude only. For example, someone says that there's a guy and he took 5 seconds to answer a question, right? It was shown in MCQ and it took 5 seconds to answer that MCQ. Now 5 seconds, we understand second is the unit of time, so we are measuring a physical quantity time, and the value of that physical quantity is second. Now do we need to explain that 5 seconds with direction? Or have you heard someone saying it took him 5 seconds upward, or it took him 5 seconds downward, or it took him 5 seconds towards north to complete a task or to answer a question? No, that makes no sense. So for those quantities with which you do not need to mention the direction, with which direction makes no sense, those quantities are scalar quantities. Time being one of them. I've given the example of time. Time being one of them, it is a scalar quantity. And vector quantities, we define them quantities these quantities are represented by magnitude and direction. So this is the extra bit. In the vector quantities, this is the extra stuff, direction. So magnitude alone is not enough for their proper description. You need to represent, or you need to give information about their direction as well. Only then we can say that we have described the vector quantities. Now, the scalar quantities, if you have to express them, for example, time or mass represented by m, time represented by small t. Alright, so these are some of the examples of scalar quantities. One of them, let's say distance, represented by d. So these are represented by normal alphabets, depending on what the alphabet, what the quantity is, and we should learn the symbols as well. This is what we study in the very first video of this chapter, that you need to learn the symbols and the units of some prominent and especially the base quantities. Time, for instance, is represented by small t, mass represented by small m. For the vector quantities, if the quantity is a vector quantity, for example force, we generally represent it by bold alphabets. There are different notations to it, okay? So we are not getting into the details of it, because according to our syllabus we don't really need much information about it. All right, that would be enough from here, that you should know scalar quantities can be represented by normal letters and vector quantities are represented by bold letters. And once again, there are different ways. There are plenty of ways you can represent a vector quantity. Graphical representation. So scalar quantities do not require the graphical representation as such, or just write none. Alright, for scalar quantities we don't really need to represent them graphically. You can, let's say if we are drawing a graph over here, we have time here, and then we are measuring speed or velocity here, then time can also be represented graphically, 1 second, 2 second, but we don't need to. Vector quantities, on the other hand, they do have graphical representation, and they are represented by straight lines with an arrowhead. Straight line with an arrowhead. And then we'll learn in the next in the upcoming slides that what does the straight line represent and what does the arrow represent for a vector. So for now you have to know about it, that vectors are represented by a straight line and an arrowhead. For example, like this, it might be representing a vector. For scalar quantities we don't need their representation like this. There are some special cases where we might be needing to represent them, but here at this stage we just assume that there's no graphical representation for the scalar quantities. Examples examples of the scalar quantities: all base quantities. So we have studied 7 base quantities in our very first video of this chapter. Some of them include time, mass. Speed was not base quantity, but that is one of the example of scalar quantity. Matter of fact, there are like dozens of scalar quantities and dozens of vector quantities. Now, how many of these quantities, scalar quantities, and how many of the vector quantities do you need to memorize? And the answer is only the quantities that are assigned or that have been demanded by the Cambridge. You can find in your syllabus breakdown as well. So here are the quantities that are explicitly mentioned in the syllabus that you need to memorize or that you need to be able to answer, whether they are scalar or vector. So for the scalar quantities, these are the ones that are mentioned explicitly in your syllabus, and apart from that, they also ask us about some other quantities that are scalar, for example area, surface area, cross-sectional area, any kind of area, volume. These two are also frequently asked, and these are also scalar quantities. Especially for the vector quantities, uh, these are the vector quantities that you need to memorize, and you would be required to recall the fact that these quantities are vector quantities. And I'll show in the sample questions as well, like what kind of questions do you exactly get from here. So these are some of the differences that we have studied between scalar and vector quantities. And one of the thing is, I often tell it to my students that if they are prone to forgetting or to confuse scalars with vectors and vector with scalars, like which one does require the mentioning of direction, so they can keep this thing in their mind. VDM, sorry, DVM. All right, so DVM, a popular word, uh, popular mnemonic abbreviation. That's a program, study program as well. So in that way, you can understand that direction, vector, magnitude. So the center one vector, it has direction as well as magnitude. So this is one way of memorizing. You can another way you can memorize it that way as well, but this is a thing that is on your end. The faster you memorize it, the examples, the better it is for you. Moving on to some of the sample questions. So this is the kind of questions that you get from this topic. And in this one, like the first one says, which quantity is a vector? Speed, force, mass, distance. Now you go back to the table, back to the quantities where I've mentioned these quantities, and over there you realize that force was also mentioned in the vector quantities. So you can safely encircle part B, that is force. So force is a vector quantity. A story investigates the motion of a ball falling through the air. Which quantity is a vector? Once again, gravitational force. Force is a vector quantity. No matter what kind of force it is, it would always be a vector quantity. Force can be of different types: gravitational force, electrostatic force, magnetic force, right? Mechanical force, any kind of force, it would be a vector quantity. The next one says, which row correctly shows example of a vector quantity? So vector quantity to be represented in left column and scalar quantity to be represented in right column. So it cannot be A because force is not a scalar. It cannot be B because mass is not vector. It cannot be C, once again velocity is not vector. Velocity is vector, but acceleration is also vector. And it is option D. Weight is a vector quantity. Basically, you'll learn in the upcoming chapters that weight is a special kind of force. So weight is nothing but a force. Both are measured in the same units, which is Newton. But volume, this thing, like I mentioned it explicitly in the scalar section in the examples, because they keep asking about volume and surface area. These are also scalar quantities because we don't mention direction with the volume. Let's say the volume of a cuboid, the volume of a sphere is 40 cubic centimeters. Then no one says the volume of sphere was 40 cubic centimeter downward or upward. If you mention direction with it, that makes no sense. It looks very weird. Alright, moving on to the next one. Velocity is given by the change in displacement by divided by the change in time. How many quantities appear in this statement? How many vector quantities? We started with velocity. This one is vector. There's another quantity displacement. That one is vector. There's another quantity time. Time is not a vector quantity. It is a base quantity, and like I said, all the base quantities are scalar. So how many vector quantities do we have from here? 2. So C, 2 is the right answer from this one. Then we have some paper 2 questions state the difference between scalar quantities and scalar quantity and a vector quantity. So pretty straightforward. Scalar quantities, you can write this one in description. I'm just writing in bullets. Scalar quantities are represented by magnitude only. Vector quantities have to be described by magnitude plus direction. State 2 examples of each type of quantity. So for scalar, we can write mass, time. Vector, we can write force, velocity. Velocity is basically we study in detail in the next chapter. Motion, which previously we used to call it kinematics, now we call it motion. So we study in that chapter what exactly is velocity. Right now you can think about velocity as a speed in a certain direction. The next thing is vector diagram. Like in the graphical representation, I said vector quantities are represented by a straight line with an arrow. So they have a graphical representation. So a vector arrow is used to represent a vector quantity graphically. Right. So in the vector diagram, like I mentioned in the previous example as well, in the previous slide as well, in the vector diagram, vectors are represented by a straight line and an arrowhead. So the next one, if in the vector diagram the size of arrow in each consecutive frame of the vector diagram is the same. It means all the vectors have equal magnitude. Then I'll be explaining this one separately as well. A vector is represented by two things. First of all, a straight arrow. No, not an arrow, a straight line. So I'm going to cut it off from here. It is a straight line. A straight line and an arrowhead. So straight line represents, in vector diagram, the straight line gives a certain information about the vector, and that information is, it represents the magnitude of the vector. The magnitude of the vector. Now what do we mean by magnitude? Let's say there is a force of 10 Newton upward. So this thing upward is the direction. This thing Newton is the unit, and the number which is followed by the unit, that is called magnitude. So what is the value of that force? What is the value of that vector in number? That is called magnitude. So if I compare, I have a force, one force 10 Newton, then I have another force 20 Newton. I'll say the magnitude of F2 is greater than the magnitude of F1, because the number of F2 is greater compared to the number written with the F1. The arrowhead of the vector quantities represents direction of that vector. The direction of that vector quantity. Now let us take a look at the three cases. We have three very beautiful examples here that would help you clear the concept of it. So these vectors are being represented by vector diagram, by they are represented graphically. So for the first one, example number 1, we do have a vector, and you see the length of the vector A is greater than the length of the vector B. So we write magnitude, direction here. We'll be comparing their magnitude and direction for all three cases. Magnitude, direction. For the last one, magnitude, direction. Alright, let's talk about the magnitude of the first one. The vector A appears to be longer than the vector B. The length of the line is longer, so that means magnitude of A, vector A, is greater than the magnitude of vector B. So this one might be representing, let's say, a force of 10 Newton, but B would be representing something less than 10 Newton. So it might be, let's say, 6 Newton, 5 Newton, or anything like that. But magnitude of A is greater than B. What about the direction? Both lines, both the vectors are parallel to each other, so that means they are in the same direction. So direction wise, these two vectors are same, but magnitude wise, the vector A is greater than the vector B. The next thing, if you take a ruler and you measure the length of the vector A and then you measure the length of the vector B, you'll notice one thing, that they have the same length. So when I was drawing it, I just copy pasted that vector A was copied and just pasted and then over here I named it vector b, just to ensure that they must be having the same length. You can measure it with this ruler as well. So if they have the same length, then magnitude wise they are same, they have same magnitude. So if this one is representing, let's say, 8 newton, this one would also be representing 8 newton, not less or not more than that. Let us talk about the direction. Direction of the vector is represented by the arrow, where the arrow is pointing at. So this one arrow is pointing over here, this arrow is pointing over here. They have different directions, they have different direction. So direction wise these vectors are different, or you can say they have different direction. Now for the example number 3, we have two vectors, and if you measure the length, you'll find out that they have the same length. So that means their magnitude is same. And once again, when I say the word magnitude, that means the number. So if this vector is 20 newton, this one would also be 20 newton. So magnitude wise they are same, equal in magnitude. Direction, now you see these two vectors are also parallel to each other. That means they are moving in the same direction. A is moving over here, B is moving over here. So direction wise they are moving in the same direction. So from these three cases we can get a lot of information about the magnitude and direction of different vectors.